Welcome to NLA Module 2, where you'll be learning about graphing exponential functions. Our three major goals for this module is so that students can understand what an exponential function is, and secondly, distinguish between exponential growth and exponential decay in both equations and in graphs, and finally, to learn to graph exponential functions. I hope that after you've watched the video, you feel like you understand what an exponential function is. You understand the difference between growth and decay, either looking at equations or looking at graphs, and then you have a pretty general idea of how we can graph exponential functions and what they might look like. There will be a Schoology quiz that you can take in a little bit, and then there's also a little matching activity that you can do in the module right after you look at this. Good luck, everybody. So our first learning target is that we will understand what an exponential function is. An exponential function, in its most basic idea, is that maybe we double something every day. So today I give you $3. Tomorrow I double that and give you $6. The next day I double that, I give you $12. The next day I double that and I give you $24. Exponential growth, like I just described, is very fast changing. So an exponential function looks like this. It looks like y equals some constant times some other constant raised to the x power. This number right here, being an x, tells you it's exponential. Notice the x is in the exponent. All those words start with the sound x. X is in your exponent. It makes it an exponential function. Now this number that will go right here is your y-intercept. So it's where your graph is going to cross the y-axis. And this number right here is called your ratio. In the example I used a moment ago, you started with, was it $3? And then each day I doubled it. So that equation would look like this. Y equals, start with $3, but then double it each day. So notice on day 0, remember what 2 to the 0 is? 2 to the 0 is 1. So on day 0, you have $3. But then on the next day, day 1, I give you 3 times $2, 6. The next day, x will be 2. Well, 2 squared is 4. 4 times 3 is $12. So we go from $3 the first day to $6 the next day to $12 the next day to $24 the next day. You notice each day we're just multiplying by 2. Multiply by 2, multiply by 2, multiply by 2. That's what, in essence, an exponential function is. Now in the last equation, we did one, and it was an exponential growth model. Did you notice the numbers were growing each time? Exponential growth and decay have two different looks, basically. Exponential growth and exponential decay start out looking the same way. If you have exponential growth, this number right here is a number that is larger than 1. So the example I used on the other page, y equals, start with $3 and then double it each day, that would be exponential growth. Notice this number right here is larger than 1. Exponential decay, however, this ratio, instead of growing, is going to shrink your number. So what happens here is that my number has to be positive, but it's somewhere between 0 and 1. So a perfect example of this is, let's say I started by giving you $4 on the first day, but then each day after that, I gave you half as much. Notice I will actually be decreasing the amount of money I give you each day. So the first day, remember I gave you $4. That's at time 0. And then I multiply that by half to get my next day. I'm only giving you $2. The next day, I multiply that by half. I'm only giving you $1. Multiply that by half. I'm only giving you half a dollar, and so on. So the amount you're getting each day is going down. So that's what exponential decay equations look like. Now let's talk about what happens if we have a graph of an exponential growth or decay. An exponential growth model always has this look to it. We are going to have the xy axis. So here's your x-axis, here's your y-axis. All of these graphs will look the same. Going from left to right, it's growing. So as you read from left to right, what's happening? Oh, I see, it's going up. Doesn't going up and growth kind of sound similar? So now let's look at what decay looks like. Again, here's your x-axis, here's your y-axis. An exponential decay graph instead looks like this. Starting here, oh, I'm going down, down, down. Decay goes down, growth goes up. Totally makes sense, I hope. So an exponential decay graph would look like this. Now sometimes they fall faster or slower, but that's what they look like in essence. As you're reading from left to right, we're going up. That's growth. Conversely, as we're reading from left to right, if we're going down, it's decay. All right. So if we're going to graph exponential functions, what I like to do is I like to make a table. And we'll make an XY table here. And let's try with the one we started our discussion with. Let's say I give you $3 the first day, and then each day after that I double the money. So basically what we do every time we use a table is we put numbers in 0, 1, 2, and so on. And let's just see what happens. When I plug 0 in for x, I have 3 times 2 to the 0. Now remember order of operations, you raise to a power first. 2 to the 0 is 1, so 3 times 1 is 3. That's why this number right here is your y-intercept every time. Because if you raise something to the 0 power, the answer is always the same, it's 1. So I'm going to graph the point 0, 3. Now let's go back and let's take 1 and put it into the equation. Y equals 3 times 2 to the first. Well, 2 to the first is 2, so 3 times 2 is 6. So when we get over here to 1, we're already up to 6. 4, 5, 6, gosh. Okay, now what happens when we plug in 2? Y equals 3 times 2 to the second. Okay, order of operations again. What do I do first? I do this first. 2 squared is 4. 4 times 3 is 12. So when I get over to 2, I'm all the way up to 7, 8, 9, 10, 11, 12. Exponential growth, like I said before, rises very quickly. The farther this number, the ratio, is from 1, the faster it grows or decays. That's something that's nice to know. So let's just look at examples. If we have y equals 6 times 1/3 to the x, what's happening here? Let's test ourselves. This would be the y-intercept. So it's going to cross the y-axis at 6. 2, 3, 4, 5, 6. This tells us, since it's between 0 and 1, that it's actually going to be decay. And 1/3 is a bit a ways from 1, but not a lot. So it's going to, this is actually a general, normal shaped graph. Let's just do x to the first power. If I have 6 times 1/3 to the first power, 6 times 1/3 is 2, so I'm down here at 2. Let's look what happens when we raise it to the second power. 6 times 1/3 to the second power, that's 6 times 1/9, which is 6/9 or 2/3. All the way already when we get to 2, we aren't even at 1. Do you see how this is falling? So that's what that looks like. Let's just look at one more. As an example, we'll have y equals 5 times 2 to the x. And then let's look at this one. Y equals 5 times 10 to the x. Now both of these cross the y-axis at 5, don't they? Because here's a 5, here's a 5. With this one in red, when I plug 1 in for x, I get 10. 6, 7, 8, 9, 10. So at 1, I'm already up to 10. I'm just going to do a very general sketch of what's happening here. Oops. All right, let's look at this one though. This one is 10. So when I plug in 1 for x, oops. When I plug in 1 for x, I actually get 50. So I'd be way off the screen. Do you see how that one is rising lots faster? So the bigger number this is, the farther it is from 1 compared to this one, it rises a lot faster, or it falls a lot faster. So to sum it up, let's go back to our first slide.